Welcome back. This is the video for the homework solutions on Chapter 28 for Physics 104A. Starting with number 15, an industrial electric motor runs at 208 volts RMS and 400 hertz. What are the peak voltage and the angular frequency? All right, so peak voltage is square root of 2 times the root mean square voltage. And so peak voltage is going to give us 294 volts. And for part B, we want to know what is the angular frequency. So we'll do 2 times pi times the frequency given of 400 hertz, and that gives 2513 radians per second. Number 16. An AC current is given by I equals 495 sine 9.43 t with current in milliamperes and time in milliseconds. Find the RMS current and the frequency in hertz. All right, as we look at that equation, the coefficient in front of sine, that is the peak current, and the coefficient that is multiplied by t, that is omega. Now, usually, assuming we're in MKS units, which we're not, time is given in seconds, and so omega would be in radians per second. But because it says time is given in milliseconds, we have to understand that omega is given in radians per millisecond. So let's do part A. The root mean square current is the peak current divided by square root of 2, so 495 milliamperes over square root of 2, and that gives us 350 milliamperes. For part B, omega, let's first get this in terms of radians per second. So 9.43 radians per millisecond. We do the conversion, 1 millisecond over 10 to the negative 3 seconds. And that gives us 9430 radians per second. And so now we can say that frequency is omega divided by 2 pi, and that'll give us 1500 hertz. Number 18. Find the root mean square current in a 1 microfarad capacitor connected across 120 volts root mean square, 60 hertz AC power. So here's the given information. We have the capacitance of 10 to the negative 6 farads. VRMS is 120 volts. Omega is 2 pi times the frequency, so 2 pi times 60 hertz is 120 pi radians per second. So we want to know the current because the question is asking about root mean square. We're going to have to do a slight little conversion here. So let's go to the equation given in the book that peak current is peak voltage divided by the reactance, the capacitive reactance. So it's kind of like Ohm's law. There's not resistance down there, but it's capacitive reactance. And so we get peak current is peak voltage divided by 1 over omega c. And there is this relationship between RMS and peak. So peak current is square root of 2 times RMS current, and peak voltage is square root of 2 times RMS voltage. And so we can do this conversion, and we see that the peak current and voltage are related in the same way that RMS current and voltage are. Essentially, I've just substituted in these equations, and then the square root of 2's negated each other. So we have I RMS equals VRMS over 1 over omega c, and we will plug those in. Well, I've done a little simplification here, VRMS times omega c, and you should get 45.2 milliamperes. Problem number 19. A 470 ohm resistor, a 10 microfarad capacitor, and a 750 millihenry inductor are each connected across 6.3 volt RMS, 60 hertz AC power. Find the RMS current in each. So you have to understand these are separate circuits here. We're not linking them all together. I've done a conversion here that 60 hertz is omega becomes 120 pi radians per second. So let's do them separately. Let's do the capacitor first. The RMS current is the VRMS times omega times C, and we can plug in all those values and get 24 milliamperes. When we do it with a resistor, the RMS current is, this is just Ohm's law here, the VRMS divided by resistance, and you should get 13 milliamperes. And finally, when we do it with the inductor, the IRMS is the VRMS divided by omega L, and you should get 22 milliamperes. Problem 20, find the reactance of a 3.3 microfarad capacitor at these various frequencies, 60 hertz, 1 kilohertz, and 20 kilohertz. So we're looking for the capacitive reactance. And remember that reactance is 1 over omega C, and so it's going to be 1 over 2 pi frequency C, and we will plug in all those values. And so for parts A, B, and C, respectively, we get a capacitive reactance of 804 ohms, 48 ohms, and 2.4 ohms. And you can see that a capacitor has its greatest effect, meaning its largest reactance, at low frequencies. Problem number 22. A capacitor and a 1.8 kilo ohm resistor pass the same current when connected across 60 hertz power. Find the capacitance. All right, so when we have a capacitor with the AC power, it is current equals V times omega times C. When we have a resistor, current is voltage times resistance. And it says in this problem that those currents are equal to each other. So let's set those terms equal to each other. V omega C equals V over R. You can see that the voltage divides out of the equation. Let's solve for capacitance. So capacitance is 1 over omega R. So for omega, we have 2 pi times 60 hertz, or as you can see up above, I wrote 120 pi radians per second. The resistor is 1800 ohms resistance, and so we get 1.47 microfarads. Number 23, a 50 millihenry inductor is connected across a 10 volt RMS AC generator, and a 2 milliampere RMS current flows. What is the generator frequency? I've written up above the given information. We'll use this relationship that peak current is peak voltage divided by omega L, and that relationship will also work with the RMS current and voltage. So I have RMS current is RMS voltage over omega L. Let's solve this for omega. Omega is VRMS divided by IRMS L. Plug in those values, and we get omega is 10 to the 5th radians per second. The question is asking what the generator frequency is, so we should give this in hertz, omega over 2 pi, and we get 16 kilohertz. Number 39. A 2 microfarad capacitor has 1 kilo ohm reactance. What's the frequency of the applied voltage? What inductance would give the same reactance at this frequency? And how would the reactance compare? How would the reactances compare if the frequency were doubled? So we have the given information. The capacitance is 2 microfarads, and the reactance is 1 kilo ohm. Let's go for question A, which asks what is the frequency of the applied voltage? So we start with capacitive reactance is 1 over omega C, and let's turn that into omega is 1 over reactance times C. We'll plug in those values, and we get 500 radians per second. Converting that to frequency in hertz, omega over 2 pi, and it gives a frequency of 80 hertz. Now for question B. Question B says, what inductance would give the same reactance at this frequency? Well, inductive reactance is omega L, so we'll solve for L. That's the reactance over omega. So 10 to the third ohms divided by 500 radians per second, and that's going to give 2.0 henries. Up at the top of the screen, I have the given information in the blue box and our results from questions A and B in the red box. And now we go on to question C. How would the reactances compare if the frequency were doubled? So if omega were doubled, let's look at capacitive reactance, 1 over omega C, that would be cut in half. If omega were doubled, the inductive reactance, which is omega L, that would double. And so if the inductive reactance doubles and the capacitive reactance is cut in half, then the end result is that the inductive reactance, XL, would be 4 times XC. Now we could also show this with the numbers. Omega, if we're doubling it, so it was 500 radians per second, let's crank it up to 1,000 radians per second, and we can actually do the computation. We see that the capacitive reactance, 1 over omega C, when we plug in the values, gives 500 ohms. The inductive reactance is omega L, so we plug in those values and we get 2,000 ohms. And so you can see that XL is 4 times XC. Number 42 says a 1.2 microfarad capacitor is connected across a generator whose output is V equals Vp sine 2 pi Ft, with Vp as 22 volts and F 60 hertz, and T is in seconds. Find the peak current and the magnitudes of the voltage and the current at 6.5 milliseconds. All right, let's go to part A. I've simplified the formula here, so we can see that V equals Vp, which is 22 volts, times the sine of 2 pi Ft. So that's the standard format, but I've just consolidated those. So 2 pi F is omega. 60 hertz becomes 120 pi. So here's the formula we're going to use. Now, question A says find the peak current. Well, peak current is the peak voltage divided by the capacitive reactance, which is peak voltage times omega C. And we have all the values there, 22 volts times the 120 pi for omega times the capacitance is 1.2 times 10 to the negative 6 farads. And we get 10 milliamperes. Now for question B, it's asking what are the voltage and current at a particular time at 6.5 milliseconds. So we're just going to plug in 6.5 milliseconds into the voltage formula. So we have V equals 22 sine, and the thing we're taking the sine of is 120 pi times 6.5 times 10 to the negative 3. And I give this warning here, your calculator must be in radians mode, because when we take the sine, cosine, or tangent, and it's not explicitly stated degrees, it means radians. And so we do that, and we get 14 volts. For question C, we're going to use equation 28.4 in the book, and recognizing that current leads voltage by pi over 2 radians. So here we have that current is the peak current times sine of omega t plus pi over 2. And I'm not going to use it here, but just recognize that that is peak current times cosine omega t. That came up in the lecture. But let's fill these in now. Peak current is omega times c times peak voltage. And then we have the times sine omega t, so 120 pi times 6.5 times 10 to the negative 3, that's your omega t, and then plus with that phase shift of pi over 2. And so we plug all those in. Here I just wrote sign with a squiggle, meaning sign of all that stuff that I didn't care to write again. And we get current is negative 7.67 milliamperes. The question asks, what is the magnitude of the current? So even though it's going in that negative direction, it's appropriate for magnitude. Just take the absolute value, and we get 7.7 milliamperes. And that is the end of this video, the homework solutions for chapter 28. I hope you all have a great day.